for example. Deciding on a gate set depends on which gate the hardware designer is happier building because it may be cheaper or simpler in their specific case. In quantum computation, there are many possible universal gate sets that must include at least one single qubit gate and one 2-qubit gate. The selection of gates depends on which operations are possible on the hardware of your choice. It depends critically on implementation and can even change for different designs within the same technology. Another constraint introduced by the hardware implementation is the selection of qubits which can directly undergo 2-qubit gates. Some technologies require 2 qubits to be physically connected or adjacent in order to undergo a 2-qubit gate. This is typically the case in superconducting qubits. In others, it's not required. For example, trapped ion quantum processors have a long-range coupling that doesn't require them to be directly next to each other. In neutral atom computers and elsewhere, there is even the ability to change the connectivity during the runtime of the algorithm, but that's already going beyond the scope of this video. In general, the lower the connectivity between qubits, the more swap gates are required to be added to the circuit to perform its function. This increases both the circuit depth and the amount of 2-qubit gates needed. Because each operation introduces noise to the circuit, until we have a fault-tolerant quantum computer at least, this has the effect of making the circuit perform more poorly. Synthesis involves taking the high-level description and making concrete circuit implementations based on the above-mentioned constraints. There are many competing technologies in the current world of quantum processing units. There's neutral atoms, silicon qubits, superconducting qubits, trapped ions, NV centers, to name just a few. It's the zoo of qubits, which is an expression I don't like, but I am willing to use it because I do believe some of them are cute but useless, some are scary and bite you, and it's very likely most of them will be extinct soon. So some QPUs are ahead in the race, others show future promise, and as is the case in classical silicon computers, maybe only one will stay with us in the future. But we won't go into more detail now. One thing we can say is that typically, as of today, the number of qubits available via quantum clouds is larger for superconducting qubits than those of trapped ions. Thinking about the circuits we get due to the different ways a circuit is synthesized for different hardware targets, we probably will get different circuits. How do we reason about the results and decide what to run and how to tweak what we got? Circuit depth is the number of gates performed on a qubit involved in the circuit. Because gates are not perfect, each gate operation introduces errors. Some coherent and some incoherent, which we call noise. 2-qubit gates are typically much more difficult to perform and therefore introduce more noise than 1-qubit gates. When looking at the results of circuit synthesis, we can look at depth, we can look at the number of CNOT gates or other 2-qubit gates and compare what we get from different hardware targets. The Classiq IDE gives us this information very clearly and allows us to make comparisons. There's also cost considerations. In many providers, the cost depends on the number of gates, where the price is different for 1 and 2-qubit gates. In other, the price relates to the total time taken to the circuit to run, and this depends again on the number of gates. In general, the execution price of the same circuit may change dramatically between different providers. As expected, the synthesis engine chooses an implementation that uses more auxiliary qubits to reduce the CX gate count. Now, let's limit the width to 11 qubits. As a result, the synthesis engine chooses an auxiliary-less implementation. As expected, the CX gate count is higher due to the additional hardware restrictions. Let's discuss a more advanced example. This implementation uses many auxiliary qubits to reduce the CX gate count as much as possible, just like we saw previously. Now, let's ask the synthesis engine to generate the same MCX gate, but now for the IBM 127-qubit Eagle processor, a superconducting architecture with limited connectivity between the qubits, as shown in this image. The connectivity diagram is formed by vertically stacking lines of 14 or 15 qubits and connecting them via alternating 4-qubit layers. We select the quantum device and synthesize the circuit. It takes a bit longer due to the qubit routing involved in the circuit compilation process. The resulting circuit now uses 75 qubits only. Let's explain this result. As explained in the previous lesson, forming an entangling gate like CX between indirectly connected qubits requires routing the qubit state using swap gates. And each swap gate costs us 3 CX gates. Gate-level compilers perform optimization passes to reduce this number of necessary swap gates. However, this example shows that a turning point still exists, resembling the classical case. Using too many auxiliaries results in routing overhead bigger than the gain obtained from temporarily storing the quantum computations. Note that this result doesn't mean that the best possible implementation of MCX for this specific hardware consists of 75 qubits. It tells us that this is